getting started. Hi, Mish. Hi, Yeet. Your timer was brokey? I noticed. I was gone for like the whole time though. And hi, Wesley. And hi, Fool. And hi, everyone else. Hope everything's going well. I had like just got home and ran and got the stream all set up. And use the bathroom and everything. I'm still like not quite ready-ish actually. But I figured I'd come say hi, and I'm gonna step away for like 2 more minutes and I'll be right back. Have fun with the music. I'll be right back. Okay. I'm here for real now. Hi, Pen. I got my soup. I got my water. I'm out. I got my shoes off. And I'm ready to differentiate. Probably. Let's see here. We're having Ukrainian dinner with David's parents right now, so I'll only be able to lurk. That's fine. I hope you have a wonderful dinner. And I appreciate the lurk. Alright, let's get fucking into it. F word. Whoa. Who is that handsome kobold right there? Okay. Get myself all situated. Alright. How is everyone? Is everyone having a wonderful day? I've had a pretty good day. I did some private tutoring, went rock climbing, came home, had a nap, did some more private tutoring, and now I'm here. I shouldn't eat my soup directly in front of the microphone. Yeah, I love rock climbing. I just do like I go to like an indoor gym here. But yeah, I've been climbing for a while. I'm not like I'm not like that good considering how long I've been climbing, because I've been climbing for probably like 5 years, maybe 4 years. But I'm like a V6 boulderer, or like a 12A sport climber. Maybe 11, like 12A, 12B top rope, if I've practiced the route. And maybe like 11C lead climb, if any of you know what that means. Hey, Wire Dude. I am a boulder. That's what I said. Correct. Okay. Let me get the book open here. Not now. I wonder, does this have like a dark mode? Night mode. Oh. What the heck? The answer is not really. Green mode. Okay. So, it's been a minute, but allow me to remind you all. So we've done a review of pre-calculus, and trigonometry, amongst other things. And we have, so far, in terms of like the actual calculus portion of things, we've talked about limits. And so we've talked about like, what does it mean to take the limit of something? And like, how do you evaluate a limit? And like, what is a limit? And like, you know, to what limits will humanity rise before their downfall, etc., etc. And so now we're going to combine some of those pre-calc elements with that new idea of the limit. And we're going to hopefully approach the idea of the derivative today. And so, as far as, I guess kind of to recap, part of one of the things that we're concerned with or that we're wanting to do, like one of the things that we're wanting to figure out is basically like how to find like the graph, or like how to find like a tangent line to a graph. And so like we know well enough, oh, I gotta log into Desmos. Whoa! Holy shit. Whoa. So we know well enough how to, you know, if we have some graph. Ah! Hi Nightcrawler, hi Generic. We know how, if we have some graph, to figure out basically like what is like the slope of a line that goes through that graph. Not necessarily like a tangent line, but we talked about this idea of something called the difference quotient, where, here, let me write it down here. Usually the difference quotient is written as f of x plus h minus f of x all over x plus h minus x. And x plus h minus x on bottom is just h. And so this is f of x plus h minus f of x all over h. And so what is this? Well, this is, so this right here is the function evaluated. So this is like f, here I'll just write f at x plus h. And then naturally this down here, well, it is x plus h, and so it's this point. And so it's this input value. And then same thing here. On the other side, we have f of x and x. And so this is f evaluated at x. And then this is that input. And so if we compare this to the formula that it's actually kind of representing, which is y1 minus y2 over x1 minus x2, well, we kind of have the same thing. This is the output of the function at that point, and this is its input. And then this is the output of the function at another point, and its input. And so basically it's just change in y over change in x. But really it's kind of like on top here, it's really like we have change in f of x, and then on bottom, we just have change in x.
Why is chat so cute, exactly? Explain yourself, Kobold.
That's a good question. We will now expound upon that question. Take it away, Evil Talos.
Oh well, isn't it obvious? Chat is cute because they have a knack for providing endless entertainment, are almost as devious as me, and they all give such good head pats. But remember, being 2 feet tall, I'll never admit how adorable reaching for the evil plans on the fridge can be. Maybe 7 can give me a hand or a claw. In the meantime, don't let Shinikaba discover our secret plots. And thanks to the banana milk, I'll need another word for when you hold claws with people. Yep.
Why is the banana milk responsible for that? If you drink banana milk, are you not allowed to talk about holding hands? And so ultimately, all this is here is the slope. And so this is the slope of a function. But particularly, it's the slope of a function, you know, at some point x, and then it's measured from x to some point like a little bit further away, like h away. And so that's kind of what we have here on this graph. And so here we have like our x point, and then this orange point is kind of where...
Dr. Sex is too powerful, we can't stop him.
Who?
Dr. Sec.
Oh. Thank you. For clarifying that. So we have our point, like on our graph, and then we measure another point some distance h away. And so you can see over here on the left side, if I just change the h. Here, let me turn this down a tiny bit. Too much. And so what we get is a line that's going through our function with this slope. And so we can see the difference quotient that I've plugged in here. And the idea here is that as h gets closer and closer to our initial point, it gets closer and closer to looking tangent. And so right now, if we like zoom out, then to the naked eye, this would appear to be tangent. But if I zoom super far in, then you can see here that the blue line does actually cross above the white line. And so it's not tangent. For it to be tangent, it would need to cross through the line at a single point. But then we have a problem. If I bring h on top of the value we're measuring the slope at, it's undefined. Because if h is 0, then we can see in our difference quotient that we have a problem, because we would be dividing by 0. And so this is where the limit comes in. And so for us to actually figure out what this slope would be at this point, at a single point tangent to our graph, well, we need to figure out effectively what is the slope approaching as h, the distance between the 2 points that we're reading them at, approaches 0. And so like as these 2 points get closer and closer together, the slope gets closer and closer to being the slope of a line that's tangent to the function. But in its current form, h cannot be 0 because dividing by 0 would make that slope undefined. And so that's where the limits come in. You know, we talked about the last time we met, you know, like 3 weeks ago, about how you can use limits to evaluate like functions where they have discontinuities. And so even if the function is not defined at that point, you can still take the limit, assuming that limit approaches a value at that point. And as long as it approaches the same value from the left and the right. And so that's the plan. And so if we were to do like a simpler function, something like x squared, then we could see, okay, well, if I want to find the slope of the function, or the slope of the tangent line to the function when x is equal to 2. So if I make a 2, well, then we can see it's going through this point, and we want the distance between these two here to approach 0 so that we can hopefully figure out what the slope of this tangent line is. And so to do that, we're going to have the limit, the limit as h approaches 0 of, if we're doing it at 2, it would be 2 plus h all squared minus 2 squared all over h. And so as it stands, we still can't just plug h into this, because, or 8, like 0 in for h for this, because if we do, then on top here, 2 plus 0 is just going to be 2 squared, and then minus 2 squared, and then we would have 0 on bottom, so we would have 0 on top and bottom, which is indeterminate, which tells us that, you know, in its current form, we can't actually figure out this limit unless we change something about it. And so we can, you know, on this top here, we can go ahead and multiply these out and expand these. And so this will be the limit as h approaches 0 of 2h times 2h, or 2 plus h times 2 plus h, which is going to be 4 plus 4h plus h squared. And then we have minus 4, and then all over h. And now this is looking good, because this 4 and this 4 will cancel each other out. And then what we'll be left with is the limit as h approaches 0 of 4h plus h squared all over h, and we can factor an h out of the top. And if we do that, it will cancel with an h on bottom, because this will be h times 4 plus h. Yeah, it's 4. And so if we have the limit here as h approaches 0 of h over, or h times 4 plus h all over h, then we can cancel out these h's. Then we just have the limit as h approaches 0 of 4 plus h. Well, now we have no problems just plugging in 0 for h to figure out what this equals. And we can do that, and we find that this limit is equal to 4. And so kind of going back to, once again, kind of what we're doing here, we're taking the limit as h goes to 0 of the difference quotient of this function, x squared, when x is equal to 2. And so basically we're figuring out, you know, what is the slope of this line as h gets close, like as h approaches 0, as this orange point gets closer and closer to this blue point. And so normally, like if they were on top of each other, we wouldn't know. But now we know, through the power of limits, that the slope of this line is in fact 4. And so of course it won't be exact, but you can kind of see when they are really close to each other, it does look like this line has a slope of 4. If we go up 4 over 1, and then up 4 over 1, it seems to match really closely. Of course, if we go further and further away, it will kind of drift away. And so, without this being exact, we wouldn't be able to tell. But I can actually create like another function here. And so this would actually be, if we just do 4 of x minus a, and then f plus a, then you can see we have this new line. And you can see if I zoom in on this point right here, if I just keep this point on, if I zoom in on this point right here, then we can never like find a point where like it's not matching. Like if I start up here, then you can see like there's a gap between them, but as I get closer and closer to like the blue point, there's never a spot where like it crosses through another point on the function. Thus just kind of like reinforcing that this point, like that this line that we have here is a tangent line. And so that's all well and good.
Evil Talos, can you take over good Talos so he ends this calculus stream pretty please?
What, you don't want calculus?
The temptation of ending Talus's calculus stream early is strong, but I'm currently preoccupied. My plans are stuck on a fridge taller than me, thanks to Zez's hijinks, and a secret agency is snooping around. Plus, I'm a bit busy sipping on banana milk and thinking about lobsters. Besides, math is the perfect cover for world domination, so let's just admire your cuteness and plot some more. Yep.
That's right. And so sit down and get your math. We need it for world domination.
I like math, okay?
It's true. You do. And so that's great. We figured out how to find the graph of a tangent line for like a single point. But can we do this in general, I wonder? And so what if, instead of, asking about like, okay, well, what's the tangent line whenever this is equal, like whenever the function is equal to 2, well, what if we just plug the function in general? And so what if we did the limit as h approaches 0 of x plus h squared minus x squared all over h. So now we're doing the limit as h approaches 0 of the difference quotient where we've just left it in terms of x. And so hopefully what we'll get whenever we complete this is a function in terms of x that tells us what the slope of our original function is at any point. That would be cool. And so let's go ahead and figure this out. And so this will be the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. And we get a very similar situation. These x squareds cancel each other out. And then on top we have 2xh plus h squared, which we can factor that h out. And so this will be the limit as h approaches 0 of h times 2x plus h all over h. And so these h's can cancel. And then we just have the limit as h approaches 0 of 2x plus h, which is just going to be 2x. And so apparently, if we have the function of x squared, so the slope is always 2x, what? Well, let's figure it out. And so if I change this, so if I replace this 4 with 2a, so where a is our x value, and I turn back on this point here. Here, can I turn off the orange point? Yeah. So now you can see, so what I'm plotting here is this line where the slope of this line is 2 times whatever the the x value of this point is. And you can see it tracks along the line and always stays tangent. So yeah, the slope of the line tangent to x squared is equal to 2x, whatever that x value is for that point. Check that out. What if we do it for a different function? Like what if we do it for, I don't know, what's another one that's relatively simple to do? Let's see. Book, help me. So yeah, you can see here if we kind of go through the book, here they mention we have the slope of a line and we have that difference quotient. They use different things. I use x and h. They use c and delta x. But it's the same concept where the difference quotient represents the slope. And so if we let that difference between the 2 points that we're evaluating them at approach 0, we get the slope of the tangent line. And so let's go down here to the questions. at the end and see if we can do a couple other of these and graph them and kind of help build up that intuition. Let's see. Okay, let's do this one. 1 over x minus 1. So we're just once again going to try and figure out what the difference quotient here is. And so this will be the limit, or basically we're gonna take the limit as h approaches 0 of the difference quotient. And so this will be 1 over x plus h minus 1. Is that what it was? And then minus 1 over x minus 1. I know all this, but I lack so much intuition. I mean, hopefully that's what, I'm here to kind of help us build up today, kind of like having all of these ideas and kind of knowing sort of the, I don't know, kind of like understanding them a little more fundamentally so that it's easier to help build up that intuition. So here with this one, if we're going to simplify this, we're going to need a common denominator.
And prosperity of our sovereign nation, I need to see you juju on that beat.
What? And so it's going to be a bit sloppy, but we're going to need to multiply each of these functions, or each of these like rational functions in the numerator by the other one. And so we're going to have to multiply this one by x minus 1 on top and bottom. And we're going to have to multiply this one over here by x plus h minus 1 on top and bottom. Maybe there's a simpler way to do this, but this kind of looks like the most straightforward way to me. And so this will be the limit as h approaches 0 of x minus 1, and then we'll have minus this on top, and so minus x plus h minus 1 all over these two guys multiplied out. And so I guess we'll multiply that. Or do we have to, I wonder? What if I just keep it in this form? And so x minus 1 times x plus h minus 1. And then this is all over h. And so if we distribute this negative through here, this will be minus x minus h plus 1. And that's nice. Again, we get these x's canceling out and these 1's canceling out. And so then what we have at this point is the limit as h approaches 0 of negative h all over x minus 1 times x plus h minus 1 all over h. And so what I can do is I can rewrite this numerator here as negative h times 1 over this garbage. And then I can kind of write it off to the side. And so that will hopefully make it easier for you to see that this will be the limit as h approaches 0 of negative h over h times 1 over x minus 1 times x plus h minus 1. And here we get this problematic h on bottom canceling out again, which is great. That's kind of what we were looking for. And so these just end up being negative 1. And so this will be the limit as h approaches 0 of negative 1 over x minus 1 times x plus h minus 1. And now there's no problem with us just plugging in h equals 0 to figure out this limit. It won't lead to us getting an indeterminate form. And so this will be negative 1 over x minus 1 times x minus 1. Or that will be negative 1 over x minus 1 squared. And so let's check that out. And so if that's true, then if we have 1 over x minus 1, so we would have this white function here. And then if I type in that the slope is negative 1 over x minus 1 all squared. Oh, it should be a minus 1 all squared. Because this blue point is evaluated at a. Check that out. As I drag this point from left to right, this blue line hugs our original function. And so it's like it's always kind of staying tangent to it. And so you can see that here, whenever it's really steep, the line is really steep. And whenever it's really shallow, the line is really shallow. It's the tangent. Wait! I'm waiting. Are we having a learning moment? I'll take a bite of soup. Why has my brain never put together that the tangent of a circle is probably related to tan x? I don't know that it is, necessarily. It's kind of more like if you have... There's like a geometric interpretation of what the tangent function is. And it is like a portion of a line that would be tangent to a circle. But they're called the same thing. I mean, frankly, I don't know why the trig functions are called sine, cosine, and tangent. I'm sure that there is a connection, but I would need to research it further. Are you accepting random questions, or do they need to be about derivatives? In theory, I'm accepting, like, random questions, like homework help related stuff. Ideally, it would be related to calculus. Don't want to go on like too deep of a tangent or anything. But I'll be here all week. So yeah, isn't this cool? And so now we have a process to go through to help us figure out what the derivatives, or rather what the slope of these tangent lines are. And so, uh-oh. What are the values of a and b, or what values of a and b minimize the purple integral, and why? Oh. If this is the, in other words, the best fit line of sine of x to between 0 and 2 pi. Interesting. Something about like my brain's intuition is like would be like the point of symmetry, And so it would be, well, I guess that then you can change the value of A. And so my expectation here is that B would be equal to 0. And then A would be equal to, I don't know, like pi over 4 or something. For no particular reason other than it just feels right. Oh, what about like pi over 6? Okay, yeah, there does seem to be like a small value of B that would increase it. I'm sure that this is like an optimization problem that you could figure out. But you would have to, you would need some form of like extra constraints on A and B to relate them to one another or relate them to X. To be able to do that easily. I'm just thinking like if you were to... Well, I'm just thinking like how I would like figure it out. I'm sure that there is some strategy or some like technique that could be applied that I simply just don't know. But you know, it's like the idea is that like if you could differentiate this with respect to A, then you could find like the local minimum in terms of A. But then if you did that, then it would be the local minimum in terms of A for that value. Or like for that given value of B. I don't know, maybe you could parameterize this and take the gradient and then find the minimum as like a multivariable calculus problem. Let's see. We could figure out like, I don't know, it would be weird to figure out what this antiderivative would be equal to because it would always be like piecewise in terms of like these parts that are being flipped and these parts that aren't. Let's see. If we have our from 0 to x equals pi over 2 range, you end up having to know where ax plus b equals sine of x, which is a transcendental equation. So what you're telling me is it's got no roots. Or something. That's what transcendental means, right? No algebraic roots. Right, I mean, in theory, you don't want to approximate. Okay, so if it's just the line of best fit from here to here, then keep moving, Ate, keep moving. Can we get a cat cam? She's not in her spot right now, but she might get into her spot. What's wrong with that wave? Just ignore everything outside of the green area. We're pretending we don't see it. So, intuitively, I feel like it would just be... If you measure error as square of the area, the problem is solvable, but also boring. So, like, the naive approach would be to just, like, you know, take the slope between 0 and the point at the end. Obviously, that doesn't do a very good job as a point of best fit, because it, you know, it doesn't divide, like, the area. And like, basically, like, what we're wanting here is, you know, like, we have our straight line here, and our sine function here, and we're essentially finding the differences between, like, the areas between them. You know, it's interesting to me at all that I guess that like for this given circumstance here, that this point seems to have the lowest value. Just because like visually, I would look at this and say like for this value of A, this doesn't like look like a particularly good line of best fit. Like just like intuitively, like this looks like a little bit like better to me. But I guess it's just because like right here, it passes through many more points. Can I make the step smaller? You can change the slider params. You mean like these? Maximum fineness. Okay, and so something close to pi over 2. And so, like your 0.64. Yeah, it does get lower. I don't know. I do feel like there are probably some like approaches to calculus I don't know that there's just necessarily like a clever intuitive answer. Originally, I thought we were doing it like my brain was thinking from negative pi over 2 to pi over 2. And I feel like in that instance, you definitely would just want b equals 0 and then find some value of a. But I mean, I think that's, you know, a simpler problem. I can't imagine that there's any value of b that would improve this. But of course, when you restrict it from 0 to 2 pi, it's a totally different idea. Soup. Okay. Well, anyways. Back to simpler stuff. So, rewinding a little bit. Helps you if the interval is around 0 and odd. Yeah, and the function is odd. Yeah, maybe it's kind of like a, I don't know, there's always the idea of like, start with a simpler question and try and like expand upon it. And so, I mean, I am curious, you know, if it would be easier to find like the value for this like if I okay, so this is an aside, but if I fixed the value of this to be, if I fix the value of b to be 0, then this would be the derivative of ax minus sine of x dx, which if I evaluated this just as an indefinite integral, would be a over 2x squared plus cosine of x. And then if I took the if I took the derivative of this with respect to a, right. Right, because the sign probably would change. Yeah, and this is what I was thinking earlier, where it's like, well, the piecewise parameters of how you evaluate this changes. I mean, wouldn't... is... Well, let me think about this. Yeah. I tell you, what do you want? You've been fed. I've fed you. She wants math. There seems to be a smaller value higher than pi over 4. I would feel like I would want to start by trying to figure this out, because at least this seems like simpler in premise. Okay, let me figure out what the cat wants. Yes, hello, Ate, can I help you? Let us go. Food. Natalie. But the absolute values really mess with that? Yeah. I mean, technically, we could instead describe this as, you know, the square root of the function squared. But then that's a really... Yeah, does that help? I don't know. I don't know. I was thinking if there is anything helpful about like the version of the function that doesn't have the absolute value. Hello? But I don't think there is, because I think it's just always 0. No matter what the values are, so... But I was like, since this is technically like a multi-variable problem, like part of me feels like if you could like, I don't know, somehow have like, you know, we have our X and Y space, but then you would also have like an A and B space. And then like you'd have to do like a 4th dimensional parametrization problem. And then maybe you could take the gradient of it. The gradient fails to exist when the value switches signs? Damn. Yeah, I mean, I guess technically it's not differentiable at these points. I think this is why statisticians use error squared instead of absolute error. Yeah, I guess that does make a big difference, because if it was just squared, then we have a whole lot more techniques to use. And now it's differentiable on its whole interval. But who knows? Maybe if you bash your head against the wall long enough, you'll develop new techniques of working with integrals of absolute values of things. Part of me feels like it should be possible. I mean, like, maybe like there's some sort of like rigorous, like stochastic, like process where you jiggle the values of A and B until you like settle into a local minimum. But I feel like that's usually kind of less of a rigorous process and more of just like a less of a rigorous process and more of just like a, you know, numerical like an analytical process. The derivative of borscht x is borscht. I thought the derivative of borscht was beets. You use beets to make borscht, right? Can you split the integrand? What are we looking at out of curiosity? Jeff had this this problem where basically it's like we have this purple function, which is the absolute value of the difference between this linear function and the sine wave. And then the question is, what are the values of a and b that minimize basically this difference between the two? And so basically what would be like using the absolute value of the error between these two functions to find the line of best fit. And it's supposed to be between 0 and 2 pi. But, you know, in theory, it's like, think about an easier problem first. At least with negative pi over 2 to pi over 2, I feel like it's almost certainly like b is 0. The best fit line to sine of x is always its Taylor expansion? Yeah, but like, wouldn't the Taylor expansion also be non-linear? I guess not if you're plugging in the values of those points. I don't think that you can split this integrand easily. Unless you like put certain constraints on the values of a and b. I mean, I feel like we can be relatively confident that a and b on this interval are both going to be positive values. And x on this interval is also always positive. But the difference between the two is not always positive. I guess that's the point.
Meow, 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 meow.
Good point. Good idea. I guess let's... I think I'm gonna jump back over to here for a little bit to standard Calc 1 stuff. So we've got this idea now of using limits to find what is the slope of a function at a single point. And so you can almost think of this like the instantaneous rate of change.
I saw a fish in that last one.
Fish? Maybe is this the fish? Fish, and then fin? I don't know. And so this idea or this process of finding like a function that gives us the slope of a tangent line by evaluating like the difference quotient of a given function. This is called, like, this function is called the derivative. And so the derivative of 1 over x minus 1 is negative 1 over x minus 1 squared. And so this is how we define the derivative. And so the derivative is this function who gives us the instantaneous slope of kind of our initial function. And so let's see, the book says, you have now arrived at a crucial point in the study of calculus. The limit is used to define the slope of a tangent line, is also used to define one of the two fundamental operations of calculus, differentiation. And so the limit definition of the derivative that we've covered as follows is they write it as f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And so provided the limit exists, for all x which this limit exists, f prime is a function of x. And so whenever we talk about differentiation or derivation or the derivative, what we're talking about is the function or the process of finding the slope of a tangent line. And so this is really helpful because is derivative and differential the same thing? They're related. And so if you talk about like a differential equation, then that is like an equation that is like in terms of derivatives. Suppose x on the interval minimized the difference . Ax plus b minus sine of x would be minimized when its derivative is 0. Use fundamental theorem of calculus and bam, you numerical approximate your solution. Yeah, but Jeff wasn't wanting to do numerical approximation. Then he should make up better questions. Yeah, that's also a good point that, at least I hadn't tried it, but Jeff said that ax plus b equals sine x is transcendental. Okay, bye. Bye, pen. Jeff only likes questions that are too hard to solve. Well, that's good. I mean, you know, too hard to solve is how every unsolved question starts, right? Because for it to be an unsolved, I guess in a sense, for it to be an unsolved question, someone has to try to solve it. And only, you know, then do we know whether it's hard or not. I don't know, sometimes people are like, yeah, this question's probably really easy, and it's probably not that hard to solve, but I'm just not going to do it. That probably happens too. Let's check out some more derivatives. Let's look at the square root of x plus 4. And so if we wanted to figure out the derivative of this, then once again we're going to do the limit as h approaches 0 of the square root of x plus h plus 4, and then minus the square root of x plus 4, all over h. Let's see. How should we go about solving this one? I don't know, maybe multiply the top and bottom by the conjugate of the top? Let's see what that does. X plus h plus 4, and then plus x plus 4 over square root of x plus h plus 4 plus square root of x plus 4. And so we know the cross terms will cancel each other out, and so it'll just be this squared plus minus this squared, and then we'll have all this nonsense on bottom. And so this will be the limit as h approaches 0 of it'll be x plus h plus 4 minus x plus 4, or rather x minus x minus 4. I'll write it like that. And then we have h times the square root of x plus h plus 4 plus the square root of x plus 4. And so we have now effectively unrationalized this function. And so all Algebra 2 teachers are weeping in pain. And so we can see that the x's cancel out and the 4's cancel out. And then that leaves us with just this h on top that can cancel out with this h on bottom. And so that's perfect. And so now we have the limit as h approaches 0 of 1 over the square root of x plus h plus 4 plus the square root of x plus 4. And so now if we plug in like h equals 0 for this, then we'll get 1 over the square root of x plus 4 plus the square root of x plus 4. And so that's just going to be 1 over 2 square roots of x plus 4. So let's check it out. And so if we have the square root of x plus 4, and then I make the slope of this line 1 over 2 times the square root of x plus 4. Oh yeah, it's got to be a. It's got to be a. then that looks pretty good to me. And so of course, if we make a too small, so we go beyond the bound of the function, then it doesn't work. But if we're plugging in the values, where the function is defined, then it does work. And once again, we can see that this is the tangent line. If we kind of zoom in on this boundary here, then, of course we can't like zoom in really like far enough, but to an extent, like you're gonna have to trust me. But like this is the tangent line. And you can see as we kind of move it along the function, it hugs the function and stays up against it. And so wherever the function is steep, the line is steep, and wherever the function starts to get shallow, the line gets shallower too. Can you do the log x derivative that way? Like with using the limit definition? I don't know. Let's find out. Maybe not. If you're asking me, I'm going to assume that maybe I can't. But only one way to find out. And so the limit as h approaches 0 of the log of x plus h minus the log of x. And so I guess let's find out then, why can't we do it? Where's Ate? It turns out she wanted to go outside. And so Ate is outside right now. Let's see. Outside where? She's probably like just sitting in the backyard, or she's like on the roof or something. Right, so we could combine these into a single log. I wish my cats would go out. I can't even stretch my toes because Kit Kat is at the foot of my bed and being mean. Your cat's name is Kit Kat? Yeah, I know that I shouldn't let her out. I tried to convince her to be an inside cat for a long time, but she wasn't happy. And so I'm just gonna have to deal with the ramifications. So can we actually, can we exponentiate the whole thing? Because we would need some way to undo it. I mean, so for the, if we make this like the natural log for simplicity, right, but we already have like the natural log. Like this is an expression. And so it's not as though we can like take the power of both sides. Like we can say that, u is equal to like the natural log of e to the power of u. But if you have the natural log of u just as an expression, then you can't simply just raise that to the power of e without also like taking the natural log to kind of like preserve the question algebraically. Okay, do your magic and get those H's to cancel. Okay. I'm on it. Let's see. If we... let's explore. That's what we're here to do. So if we have the natural log of x plus h over x over h, then that would be the limit as h goes to 0 of the natural log of 1 plus h over x over h. X plus 1 to the power of 1 over x as x goes to 0 or something? I don't know. And so, in my head, I'm thinking that I don't know, maybe we do something with the h on bottom. And so if we made this like the limit as h goes to 0, as the natural log of this business. What if we make this the natural log of e to the power of h? I don't know that we can do much with that. I guess, I mean, we could use change of base. Base h? Technically it would be like base e to the h. Hold on, that's actually kind of an interesting idea. Because if we have the limit as h approaches 0 of this would be log base e to the power of h of 1 plus h over x. But e to the power of h is, well, if h is approaching 0, then that would just be the natural log. Because it's 0. No, it would be 1. Yeah, log base 1. Not log base e. Darn it. Does moving h in as a power work? The hth root? What's the 0th root of a function? That doesn't work, does it? So this would be the limit as h goes to 0. I can give you a clue. I would take a hint. So if this is 1 over h times the natural log of 1 plus h over x, then this could be the limit as h goes to 0 of, that's an h, trust me, the natural log of 1 plus h over x, all to the power of 1 over h. The definition of E. The natural log of 1 plus u over u is equal to 1 for a very small u, such as a u approaching 0. Can we rewrite this? How do we rewrite this in terms of like the hth root on the inside? So I do see this kind of definition of E here, where if we bear in mind that the limit as n approaches infinity of 1 plus 1 over n to the power of n is equal to E, then we could instead say that as h approaches 0, if these terms, if this term approaches 0 and the power approaches infinity, this should be equal to E. Whoa! Someone finally got the surprise VIP. No one's gotten in like several streams. Crazy. I mean, that is technically a true statement here. Like, if we had just this inside portion, how do you get it? Whenever it opens, a channel point redemption opens. Ate wants back in. Hello, Ate. The window is too short. It's intended to be for people that are actively watching the stream. Not like people who just like happen to come back and it's open. Okay, let's try this substitution then. And so if we say that u is equal to h over x, make it like a minute or two. What do I like? What? How long is it right now? Right now it's 30 seconds. I guess I could make it a minute. Is it only the first person? It's just the first person. Yeah. Or right, if we're aiming for something of the form of 1 plus 1 over n, or I guess 1 over u in this case, then should we substitute this as x over h? And so, because if we make this x over h, then we could say that this is the limit as h approaches 0 of x times u times the natural log of 1 plus 1 over u. Well, I guess then this wouldn't need to be h. Okay, well, as h approaches 0, then u approaches infinity, as long as x does not equal 0. Can I say that? And so this could be the limit as u approaches infinity. And so then now I could bring that u in, and so this would be u approaches infinity of x times the natural log of 1 plus 1 over u to the power of u. And does that, can we, so natural log is continuous, so you can pass the limit through, right? Oh yeah, this should be 1 over x. This should be 1 over x out front, because this x plus h, if I multiply this by x over x, then the x plus h becomes this u here. And so, because the natural log is continuous and 1 over x is not in terms of is a constant relative to u, then I should be able to rewrite this as 1 over x times the natural log of the limit as u goes to infinity of 1 plus 1 over u to the power of u, which we know to be the definition of E. Can I drag this in here? No, it didn't like that. And so that makes this 1 over x times the natural log of E, which is 1 over x. All right, now do arctan. I don't know. Why can't we? We did natural log. So my first thought with arctan, is that if we have arctangent, whoops, then if it's arctangent of x, then that effectively refers to some triangle where the opposite is x, the adjacent is 1, and there's some angle theta, such that the tangent of theta is equal to x over 1, and so the arctangent of x would be equal to theta. And then the hypotenuse would be x squared plus 1. And so I feel like this information will be, oh yeah, the square root of this. The square root of x squared plus 1. Mischief Managing, thank you for the follow. Welcome on, or welcome aboard. I feel like this information will be relevant to figuring out the derivative to arctangent in some way. So you'd make x side h longer to start? Yeah, I guess so. Ate, go sit down. Go get in your spot. Is this intriguing to you, Ate? Go get in your spot. Look, there's a bottle cap on the blanket. Isn't that crazy? How did that get there?
How do you manage the mischief of chat, banana milk drinking lobsters, and having your plans on top of the fridge?
Go lay down. She says, I don't
Managing
want
mischief, banana milk, drinking lobsters, and unreachable plans is no easy task, but I handle it with my trademark charm and sarcasm. Step 1. Accept that chat is cuter than gnomes. Step 2. Use 7 to access my fridge plans while wondering how Schneekebab became so well informed. Step 3.
Schneekebab?
Share banana milk and wit with chat. And if they're nice, maybe a tiny kiss. It's all about layering chaos effectively while secretly wishing for some claw holding. Yep.
He's all about the claw holding today. Yeah, sometimes he adopts an accent. Ha. 001I underscore. What a name. Thank you for the follow. What's the background music? Right now we're listening to A Safe Place to Sleep from apparently the Dust Force OST. But then there's some songs from Omori and some Legend of Zelda and a bunch of other stuff. Several games that I haven't even played before necessarily, that I just like the OSTs too. What? What do you want from me? Let's see, can I get her in shot? Alright, this is as much as you get. This is what she does sometimes. She sits here and just rubs her face on the microphone. Thankfully, my audio setup, you know, well, maybe unfortunately. Ate, can you speak into the microphone, please? You gotta speak into the microphone. All right, there you go. I don't know what that sounded like. Someone's gonna have to clip it. So, one thought that I have here is that whatever the derivative of arctan is going to be, and so whatever the derivative with respect to x, or whatever the derivative of arctan ends up being, is going to be equal to the derivative of theta. And so however this angle changes as x changes is going to be equal to whatever the derivative of arctangent is. And so part of me thinks that if we just take the tangent of both sides and start with x is equal to tangent of theta and differentiate both sides with respect to x implicitly, maybe that will get us somewhere, because then it would be 1 is equal to d theta dx times the secant squared of theta. And secant is 1 over cosine. And so this would be, let's write it as, it's sort of cheating if you use the known derivative of tangent of x. Okay, well, can we find the derivative of tangent of x then without knowing the derivative of arctan? Because then we could use that. Let's see. I think you have a general rule showing the derivative of an inverse function has a relation to the original function. Are you gonna bite my pen? This is a cat stream. How would I find the derivative of tangent? I guess to find the derivative of tangent, I would first want to show the derivative of sine and cosine. And then prove the quotient rule. Well, at this point, we may as well just get back to the book, because that's well on our way. That's what we're well on our way to doing anyways. I think Jeff is sabotaging you. It's fun. I mean, I'm having a good time though. Are people learning things? I don't know. Listen, I have to be allowed to be silly sometimes. If I can't be silly, then I will simply wither away. I actually think finding the arctangent derivative is easier than finding tangent. You're gonna loaf right there? Ate, my mouse is right there. How am I supposed to use that? You have your blanket right there. You can go sit on. Look at this dummy. Good cat. Yeah, just look up there. Okay. Let's see. Let's do some more questions. Okay, yeah, let's do one of these like simple cases. And so like the derivative of a constant. And so let's just show that too. And so if we have the limit, so considering that the difference quotient, so that we know the derivative, often written as f prime of x, like this little apostrophe. And so if that's going to be f of x plus h minus f of x over h, at least following the limit definition of the derivative, which of course I forgot my limit. then if f of x is just equal to like 7 or something like that, then we get that the derivative of f of x in this case would be the limit as h goes to 0 of f of x plus h, but there's no x. And so f of x plus h is just also 7. And so this would be 7, and then f of x is 7 over h. And so in this instance, this gets us the limit as h goes to 0 of 0 over h. And so this is an interesting case where this might look like, oh, if we plug 0 in for h, we get 0 over 0, and that's indeterminate. But if you think about it in this instance, if we allow h to start at something like 1 and then approach 0, then as the value of h approaches 0, it will just always be 0 because the 0 is on top to begin with. And so it's like there's no variation in the value. And so the limit as h approaches 0 in this instance just is 0. And so don't be like confused in this particular case of like, you know, even though it seems like it might be indeterminate, it's actually not in this case. Usually it would be indeterminate where plugging in a value for h on top and bottom causes it to be 0 over 0, but it's not necessarily the case if the top is already 0. And so let's consider what that means for a second. And so we know that the derivative refers to rate of change, and so in theory, what we're saying is that if we have a function, if f of x is equal to 7, then its rate of change is 0. And well, if you look at f of x equals 7, it's just a straight horizontal line. And so that actually makes perfect sense. And so it should be 0 because it's flat. It's not changing. It's not going up or down or anything at all. And so it's just gonna stay at 0. And so one of the kind of key takeaways from this question right here that's good to keep in mind is that the derivative of a constant is 0. Or like these cases here. We'll go ahead and do this one just because. No, don't eat that. Okay, well now I can't even read my screen. I'll wait. Don't worry. Take your time. Just know that you're taking my time too. And 17 other people's times as well. Go on. Okay. So if we do another simple case, so if we have f of x is equal to negative 10x, just to get these easy ones out of the way. Where's Maple? I demand Maple. Should I grab Maple and show you all Maple? What about Katie? Katie actually listens to me and doesn't poop on the floor. And so this would be negative 10 times x plus h minus negative 10x, which I'll just write as plus 10x. And then this will all be over h. And then this is very easy. If we distribute the negative 10 through, we get the limit as h approaches 0 of negative 10x minus 10h plus 10x over h. And then the 10x's cancel out, leaving us with just negative 10h over h. And so then we get the limit as h approaches 0 of negative 10h over h, and then the h's cancel out. And so then we have the limit as h approaches 0 of negative 10, which is negative 10. And this is another case where if we think about it for a little bit, what we're saying is the slope of a function like negative 10x, the slope of this function is negative 10 at all points. It's constant. Its slope is constant, and its slope is negative 10. And if you think about it for a moment, that makes perfect sense, because negative 10x is a linear function, meaning that it's a straight line, meaning that it has a constant slope. And so it's where we start to get the derivatives of these non-linear functions that things start to get interesting. And so then I just did. Don't you lecture me. Okay, let me go grab an animal. Let me get you guys. Let me bring a friend. She's getting so big. Look at how big these paws are. Her paws are bigger than Katie's. Mabel, look up at the camera. Look up at the camera. She's baby. She's baby. She yawned. Yeah, she's not a potato anymore. Now she's like a, I don't know, like a rotisserie chicken or something. Okay. I release you. Be free. Oh. And now we got Katie. The big chunky baby. I love her. Look up there. What a good dog. Hey, look. Look. Look, Katie, they're talking about you. Okay, would you like to go? Would you like to go now? Okay. Where is my mouse cursor? Okay. Let's do 17. X squared plus x minus 3. And so if we're saying we have f of x is equal to x squared plus x minus 3, and we want to find the derivative of this, I was playing G and B and lurking, so I don't know what's going on math-wise. Can you explain? So you were here when we talked about the limit of, like, basically finding the limit of the difference quotient. And so this guy right here. And so we've just been going through some examples. And so what we're doing now is we're using that limit definition of the derivative. And so we have f prime of x, so this is the derivative of f, which should be the function that gives us the rate of change of this function, will be equal to this difference quotient here. And so here, if I copy this, the fuck is a derivative? So we have this. So if we have like you know, some function here like x squared, and then we graph the line that has some slope tangent to that function. Where is A? Come down here. Then we can see that this line is tangent to x squared. And so the derivative, essentially the derivative of x squared is the function that tells us what the slope is at every point. And so in this instance, earlier, back towards the beginning of the stream, we showed that if you evaluate the difference quotient with the limit as h approaches 0 of x squared, which is this equation right here, you get 2x. And so basically the slope of 2x at any point, or I'm sorry, the slope of the function x squared at any point along the function is 2x. And so if we like zoom in here and we go and we put it on x equals 2, then the slope of this line is 4. If we put it on x equals 1, then the slope of this line is 2. The what quotient? The difference quotient. And so the difference quotient is basically just like the slope of the line. And so the way that it's often written is it's f of x plus h minus f of x over x plus h minus x, which the x plus h minus x on bottom reduces to just h. But this is effectively the same thing as y1 over, or y1 minus y2 over x1 minus x2. And so effectively this is just the slope. But the idea here is if we allow the limit of this difference quotient to have the value of h approach 0, then what we're saying is basically we have this secant line here. we have this secant line here, where a and h is just like the line connecting from a to h is just like a secant line of this function. And the idea is we can see that as h gets closer and closer to a, the line gets closer and closer to being tangent. And so, like, to the naked eye right now, which is them close to each other, the line looks pretty tangent already. But the problem is the difference quotient for us to achieve this has h on bottom. And so if h is actually equal to 0, you can see the line disappears, because that would be dividing by 0, which is undefined. And so kind of following up on the things that we learned, like 3 weeks ago, you can actually evaluate like what these functions would be approaching, even if they're at a point that's undefined, if you basically take the limit as you approach that value. And so what we're doing here is we're letting the distance between these 2 points approach 0, and which is ordinarily a value that is undefined, but using the limit, we can evaluate it. And so we'll be able to find what basically the slope of the tangent line will be. And that's kind of one of the main things that we're wanting to do for calculus. Because if we have an equation that tells us, I think I'm in way over my head here. I should have been listening to all the other math streams. Well, thank goodness there's a place that you can go that has all of the math streams previously recorded for you to watch at your viewing pleasure. Including this one. But the idea here is we're trying to find like the slope of a tangent line to a function, with the idea being that if you can find like an equation for the slope of a tangent line, then you know what the rate of change is of that equation at any point. And while it may not sound significant necessarily immediately, we're going to continue to learn about the different things that you can do with the rate of change of these various different like functions, if you know them. And so, I mean, like one thing that we talked about earlier with the problem that Jeff asked us about like optimizing the difference between like sine and a linear function, a lot of ways that you approach different optimization problems is to essentially take the derivative of them and then find like the point where the derivative stops changing, or rather where the derivative is equal to 0. So like where the function stops changing. And so that would be like at a point where the function stops changing, that's going to either be a minimum or a maximum. And so then you can kind of go further to figure out, okay, well, is this a minimum or is this a maximum? And then once you know which it is, then you've kind of achieved what you're looking for. You've either found the maximum that you're optimizing for or the minimum that you're optimizing for. And so it's kind of like, like a classic kind of question is like, let's say that you have 100 feet of fence. I don't want the ink to shape. And so if you have like 100 feet of fence, well, there's a couple ways you could do that. You could make that like a really thin rectangle, or you could make it a square, or you could make it, a tall rectangle the other way, or you could just make it a normal rectangle, whatever you want to do. Where, basically we're saying that the length plus the width of this rectangle is equal to 100. And we want to ask ourselves, it's like, okay, well, how do we place our fences in such a way that we optimize the area? And so we want the most amount of area. Well, that will be our length times our width will give us our area. But if we just kind of call one of these x, so if we call like our width x, then, or which one's width anyways? Let's call this x. And so then our length is just going to have to be, well, like this one would be x as well. And so this one would be 100 minus 2x over 2. Or that would just end up being 50 minus x. And so the widths are 50 minus x, or lengths, I don't know. And so then we can... Oh yeah, 2L plus 2W is 100, yeah. Of course. This is still correct, right? Yes, I think so. And so now, in terms of x, we can say that the area will be equal to x times 50x, or 50 minus x. And so that will be negative x squared plus 50. And then, if we went and said, okay, well, what's the derivative of this? Well, then we can go and figure this out. And so if we're going to say, I'm going to write it like this. So a of x is equal to negative x squared plus 50. So a prime of x, that will be the derivative of this, which is going to be minus x plus h all squared plus 50, and then minus negative x squared plus 50 all over h. And so we can FOIL this out and distribute this negative. And so this will be negative x squared this should be x. Whoops. Yeah, because the x should be distributed. What would I do without you, chat? Or at least without Jeff. And so this will be plus x squared minus 50x. And then that's all over h. And so then we can FOIL this out. And so this will be negative x squared plus 2xh plus h squared. And then plus 50x plus 50h. And then plus x squared minus 50x. And I forgot my limits. I forgot my limits. I would have lost 1 point on the test. Or depending on your teacher, maybe all of the points. And then, so this is the limit as h approaches 0. And so if we distribute this negative through, that's going to be negative x squared minus 2xh minus h squared. And then the slightly cheating here in assuming rectangular maximizes area. Okay, well, I guess I didn't say that it had to be a rectangular area. You're technically correct. If I was writing the problem for a book, I probably would have, though. That's usually the context that's provided for these types of questions. But so this x squared will cancel with this x squared, and the 50x will cancel with this 50x. And so then we'll be left with minus 2xh minus h squared plus 50h all over h. And so then we get the limit as h approaches 0. of negative 2x minus h plus 50. Do it. Do it. Lay down on the blanket. Do it. You know you want to. Go. Do it. Seize your destiny. No, you can't sit there. Go on. Would you like me to move this bottle cap? Is this bottle cap bothering you, miss? She doesn't care. And so now we can evaluate this limit, because the limit as h approaches 0 of this, well, that's just going to be negative 2x plus 50. And so now, Mish, Ate's playing with the bottle cap. You gonna bite it? And so what we've said is that the rate of change of the area is negative 2x plus 50. So if we increase this width, then the area changes like negative 2x plus 50. And so if we say, so we know that the derivative of the area is negative 2x plus 50. And so if we now say, okay, well, where is the area at a maximum or a minimum? Well, it'll be at a maximum or minimum whenever the area stops changing. One way you can think about it, it's right here. It's right there, Ate. One way you can think about it is that for something to be a minimum or a maximum, like the function has to be going up. So like for the function has to be going up, and then at some point it has to start coming back down. And that's when we get a maximum. Or if the function is going down and then it turns around and comes back up, that's when we get a minimum. And so the only way, I shouldn't say the only way, and for all continuous differentiable functions, the only way that we go from, I should say continuous smooth differential functions, or I guess just smooth. Anyways, point being, if it's a function that we can take the derivative of that we're and unbounded, then the only way that we end up with a minimum or a maximum are these points right here, where the function's going up and then it comes back down, or the function's going down and then it comes back up. But for a split moment, right at that peak, or right at that bottom of that valley, the rate of change of the function is 0. The tangent line to the function will be straight horizontal. And so those are the points that we're interested in. And so if we take this derivative and set it equal to 0, then we get negative 2x plus 50 is equal to 0. And so then negative 2x would be equal to negative 50. And so x is equal to 25. And so that tells us that if we let x be 25, that's either a minimum or a maximum. And so in this case, it's easy enough to just kind of like think about it and realize that it is like a maximum, Because if you instead just like make x 20, then that means that the width will be 30. And so this would be like our width is equal to 20, and so our length would be equal to 30. And that gives us 600 as our area. Whereas if our width and length are both 25, that gives us 625 as our area. And so that's kind of, I guess, like a taste of like the applications of derivatives. And so like one application of derivatives is, you know, using them to optimize things. So to get the maximum area out of a given, you know, system or out of a given problem that you're involved with. Let's see. So the next part goes into differentiation rules. And so the derivative rules are pretty essential. They help you kind of figure out derivatives without having to evaluate the difference quotient every time, or the limit of the difference quotient every time. I am interested in looking at the proofs for these. I don't know that I have actually done the proof of these or worked it out myself. Oh, I guess that makes sense. Wait, does it? You'd have to do like the binomial expansion here. Okay, what do they do here? If n is a positive integer greater than 1, then the binomial expansion produces this. Okay, so it is the binomial expansion. Oh, and then the xn here cancels with this xn here. Right. Because this will be the only term that doesn't have, these will be the only two terms that don't have a delta x in them. Okay, well, so I think that, I might actually call it there for today. I don't know, maybe let's look at a few more questions, actually. See if anything else jumps out at us. And then we'll kind of go deeper into differentiation and kind of some of the shortcuts and talking about the rules and stuff next week. Let's see. Ooh, these are fun problems. These ones 55 and 56. And so find the equations of two tangent lines to the graph of f that pass through the indicated point. And so this is kind of like an interesting idea. And so, so for number 55, our function is... Here, let me just grab this. So we have this function, and we want to find the equation of a line that passes through this point, and that it'll be tangent to this parabola. If I were a math teacher, I would choose to teach calculus. I think I would too. I don't think I would settle for anything less than like Algebra 2 or higher. Sometimes I like work with Algebra 2 students and pre-calc students, and I'm just like, I can't tell the difference between this material. It's all just algebra to me. Unless they're doing trigonometry. I love trig. Okay, so the idea is that, well, first off, we can find the derivative of this function, because we know that whatever these equations of these tangent lines are, the slopes of them are going to be a derivative of f of x. And so let's start with that. Let's figure out what f prime of x is. And so this will be 4 times x plus, no. Don't forget it. The limit as h approaches 0 of 4 times x plus h minus x plus h squared. And then that'll be minus 4x plus x squared. And then all over h. And this will be the limit as h approaches 0 of 4x plus 4h minus x squared minus 2xh minus h squared minus 4x plus x squared. Does ink to shape work? How does this work? You did not make a shape. I want you to make my line straight. H. And so here we can see that this 4x will cancel with this 4x, and this x squared will cancel with this x squared. And then we can cancel an h from everything on top with the h on bottom. And so this will be now the limit as h approaches 0 of 4 minus 2x minus h. And then the limit as h approaches 0 of this is just going to be 4 minus 2x. Sweet. And so now we have our derivative. And so f prime of 0, I'm sorry, f prime of x is equal to 4 minus 2x. And so then now the next part is we need to come up with an equation for the tangent lines that go through 2, 5. Well, we know the point slope form for a function is going to be, like if we write it in terms of function notation, it's going to be f of x minus, I guess I'll call it like f of a is equal to the slope, or I'll write x1 so the slope times x minus x1. And so this would be like the point slope form. Okay. And so in this case, we know what f of x1 and x1 are. And we know what our slope needs to be as well. because we know our slope has to be this slope that is the derivative of f of x, because it has to be the slope of a it has to be a slope that would make it tangent to this function either at this point or this point. And so we can go ahead and plug these things in. And so if I go ahead and add this f of x plus 1, or f of x sub 1 to both sides, then I can write that f of x will be equal to f prime of x, so that'll be 4 minus 2x, times x minus 2 plus 5. So this, I mean, this makes sense to me, but doesn't this give us a quadratic? So I mean, I know that we have two. I know that we'll have two tangent lines. Okay, well let me expand this out and let me look at this. And so then we get f of x is equal to 4x minus 8 minus 2x squared plus 2x plus 5. And so that'll be negative 2x squared plus 6x minus 3. And so then do we like factor this or something? Well, because it'll be like these 2 points, whatever these points are. Let me look at the book. There has to be like a way for us to select which tangent line we want. Let's see. What am I missing here? So we have the point slope form. We picked the values of x1 and x2, or x1 and f of x sub 1, such that we know that this is the equation of a line that goes through this point. And then we said, okay, and its slope is going to be a slope that is equal to the derivative of this function, which means we need f of x to also be a point that is on this function. Okay, there we go. And so then we can actually substitute f of x equals 4x minus x squared into this. And then we'll be able to solve for x. Because we need whatever y value this function goes through to be a point on this parabola. It can't just be any point. And so it's not just enough to restrict the derivative, we have to restrict the function as well. And so we know that the outputs of the function are going to fall on 4x minus x squared. Okay, cool. And so now if I add x squared to both sides and subtract 4x from both sides, then I get negative x squared plus 2x minus 3 is equal to 0. Is this correct? I don't like the look of this polynomial. And so this is x squared minus 2x plus 3 is equal to 0. And then if we factor this with the quadratic formula, then we get that x is equal to 2 plus or minus the square root of 4 minus 4 times 3. Uh-oh. Did I mess something up here when foiling or something? 4x minus 8. And then negative 2x squared. And then negative 2 times negative 2 is positive 4. Okay, so this should be 8x. And so this should be 4x, which is x minus 1 times x minus 3 equals 0. And so x is equal to 1 or 3. And so now we know so now we know like what are the other 2 points that our function goes through. And we know what the slope has to be too. And so we have tangent line 1. And so that's going to be f of x is equal to, what is it? 4 minus 2 times 1 times x minus 1 plus 4 times 1 minus 1 squared. And so that's going to be 4 minus 2 is 2 times x minus 1 plus 4 times 1 is 4 minus 1 is 3. So plus 3. And then for tangent line 2, it'll be this again, but with 3 instead. And so this will be f of x is equal to 4 minus 2 times 3 times x minus 3 plus 4 times 3 minus 3 squared. And so that's going to be negative 2 times x minus 3 plus 12 minus 9, so plus 3. And hey, would you check that out? I'm pleased with that. And so we have found 2 tangent lines that go through this point that are also tangent to this function. I like that problem. Let's do another. Let's do this one next. And so it looks like these are two scales, so this one looks like it's going to be a tiny bit funkier, maybe. And so we'll follow the same process here. First, we'll figure out what f prime of x is. And so f prime of x is going to be the limit as h approaches 0 of x plus h all squared minus x squared all over h. And so that will be the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. The x's will cancel. And then we can factor an h out from the top, and then that will cancel as well with the bottom. And so then we'll have limit as h goes to 0 of 2x plus h. And so the derivative is equal to 2x. And then if we were to plug this all into like the point slope form of a line, and so that will be like, say, you know, we'll have f of x is equal to our slope, which is going to be f prime of x, times x minus x1, plus f of x1. Or I guess I'll just call this like x1 and plus y1 from our point. And so we know that whatever our tangent line is, it's going to have to satisfy this, where it's going to have to go through a point on our function. But it also has to go through this point here. And then its slope also has to be a slope that would be the slope of a tangent line to f of x as well. And so if we make these substitutions, then we'll get x squared is equal to 2x times x minus 1 minus 3. And now we have to solve for x. And so this will be x squared is equal to 2x squared minus 2x minus 3. Subtract x squared from both sides. Then we are left with x squared minus 2x minus 3 is equal to 0. Ah, this again. What did I mess up this time? Oh, maybe it's minus 3 now. Okay, so this can actually be done. And so that tells us by the quadratic formula that this will be 2 plus or minus the square root of 4 minus 12, or plus 12, all over 2. And so that's 2 plus or minus the square root of 16, which is 4, all over 2. And so that will be 1 plus or minus 2. And so x... and so that, therefore, x is equal to negative 1 or 3. Pardon me. And so now, to actually get our lines, and so we'll have line, or apparently lime 1, and line 2. And so we can again use point slope form, but we still need it to fit this slope. And then it has to go through a point on this function. And so now in this case, what we're going to be using is basically it's going to be like y is equal to 2 times like x1 times x minus x1 plus f of x1. And so whatever the point is, and so like here, if this would be like x1 and x2, then we have to plug that value of x into this. So we need to know, okay, what point is it going to cross through on our function? And so for -1, we know it's going to go through this point. So this x value and this y value. But the x value it goes through is x1, and the y value it goes through is f of x1, if we decide to name it that way. And the slope is going to be the slope when you plug that x1 value into the derivative. And so then we get that it'll be y is equal to 2 times -1 is -2 times x plus 1, and then our function is x squared, and so -1 squared is just plus 1. Then over here we get y is equal to 2 times 3 is 6 times x minus 3, and then 3 squared is 9. And there we go. Those are neat problems. Kind of like stretches the use of derivatives at this stage. And then the rest of some of these are just grafting utilities and things. Okay. Well, I think I'm gonna call the stream there. And next week, we will move on to derivative rules, and proving the derivative rules too. We'll learn the power rule, the quotient rule, the product rule, the chain rule. Hopefully we'll prove all of them. That'll be fun. Well, thank you guys so much for joining me. We got anyone good to raid? Let's see. Any other math streamers right now? Math fan Brian is testing. Okay, we won't raid math fan Brian. Has he been live for 32 hours? Alright, we'll just end stream then. Must be one hell of a test. That's great. We will simply... Oops, not that button. We will... Oop, not that button either. Hello? Okay. We will simply end stream. Thank you all so much for watching. As always, I had a pleasure. If you need to go catch any of the other... Dude, you're ripped. Yeah. Yep. Yep, it's all that rock climbing. If you need to go catch any of the other math streams, they're all saved to a playlist on my YouTube channel. And so, hopefully, you learned something tonight. I learned something. And so, I see this as a total net positive. Good night, everybody. Have a wonderful evening.